Hello and welcome to the chemistry solution. This tutorial is on ionic versus covalent bonding. Ionic bonds are formed between two ions, typically between a metal and a nonmetal. And they involve the transfer of an electron to form two charged ions. So they involve the transfer of an electron from one atom, forming a positive ion or cation, to another atom, forming a negative ion or anion. So in the example of the bond formed between sodium and chlorine, sodium essentially transfers its electron to chlorine, forming a positively charged sodium ion and a negatively charged chlorine ion. And in ionic compounds, atoms will typically gain or lose electrons to follow the octet rule. Covalent bonds are typically formed from nonmetals only, and they involve the sharing of electrons between two atoms. So in the example of a chlorine-chlorine bond, instead of one chlorine atom giving its electron to the other chlorine atom, like in the example of NaCl, each chlorine atom will share one of its electrons to form a covalent bond. And just like in ionic compounds, in covalent compounds, atoms will typically share electrons in such a way as to follow the octet rule. And so when looking at the octet rule, meaning each atom is surrounded by 8 electrons, each atom gets to count both of the bonding electrons. So here, this chlorine atom is surrounded by 8 electrons, and so is this chlorine atom. These are the basic differences between ionic and covalent bonds. Thanks for watching the chemistry solution. We hope you enjoyed this tutorial.
Welcome to Dogs Teaching Chemistry. Our first lesson is chemical bonding. Chemical bonds are what holds atoms together. A chemical bond is an attraction between atoms that allows the formation of a chemical substance. The electrons that participate in a chemical bond are called valence electrons. These are electrons that are found in an atom's outermost shell. Let's take a look at the types of chemical bonds that can be formed between atoms. An ionic bond is formed when one of the atoms will lose its electron to the other atom. This results in a positively charged ion, called a cation, and a negatively charged ion, called an anion. Positive and negative attract, and the result is an ionic bond. Covalent chemical bonds involve the sharing of a pair of valence electrons by two atoms. There is also what is called polar covalent bonds. These are covalent bonds in which the sharing of the electron pair is unequal. The result is a bond where the electron pair is displaced toward the more electronegative atom. Thanks for watching, and we'll see you guys next time.
In this video, we're going to talk about polar covalent bonds. The big idea here is uneven sharing of electrons. We usually represent a covalent bond with a single line connecting two elements to each other. In this single line, there are two electrons being shared, one electron from either atom. It would seem that based on this structural formula that the electrons are being shared evenly. However, this is not always the case. Sometimes we have an element that is much stronger than another element. So it's almost like a tug-of-war going on between the electrons that are in the bond. Now, since both elements in a covalent bond are going to be nonmetals, they're both going to be pulling on the electrons, so they're still going to share. We just might have the electrons spending more time around one of the elements as opposed to the other element. Now, the measure of an element's strength is called electronegativity, and electronegativity is the ability of an atom to attract electrons to itself. Linus Pauling was the one who developed this scale of electronegativity. And his scale puts fluorine as the most electronegative element with a value of 4.0. We can determine if electrons are going to share evenly by calculating something called the difference in electronegativity, or in other words, we'll call it delta E. The delta symbol here, this triangle, means difference in. And so when we calculate delta E, we're going to compare two values or two different elements to each other. Let's try this with HCl, hydrogen chloride. So when we look at the periodic table here, we can see that chlorine has a value of 3.0 and hydrogen has a value of 2.1. So let's go ahead and calculate the difference. So delta E is equal to, we'll usually take the bigger number and subtract that from the smaller number, 2.1. And so our answer here is 0.9. But what does this mean? Well, generally, if we have a difference of 0 to 0.4, we're going to have even sharing of the electrons. We're going to call this type of bond a non-polar bond. If we have 0.5 to about 1.8, we're going to have uneven sharing of the electrons, and we call this a polar covalent bond. Finally, if we have values that are greater than 1.8, generally we're going to have an ionic bond, and we're going to have one element being strong enough or a great enough electronegativity to steal the electron from the other atom. Now these are just generalized values, and we can have some variation. Okay, so if we look back at our example of HCl here, we could see that it's going to fall into the polar range. Let's see a structural formula here for HCl. If we do that, we would end up with this for our structural formula, where they're singly bonded together. Now, since the electrons are not being shared evenly, we're going to have something called a dipole moment. And we represent a dipole moment with an arrow, with a little cross at the end, that's pointing towards the more electronegative element. In this case, chlorine. It's the stronger of the elements, and so the electrons are going to be pulled closer to chlorine. Now, since the electrons are spending more time around the chlorine atom, it's actually going to be affected by that presence of negative charges, and so it's going to have a partially negative charge. This symbol right here just means partially. Now, since the electrons are being pulled towards chlorine, that means they're being pulled away from hydrogen, and so hydrogen will have a partially positive charge. And so a polar bond means that we have one atom being partially negative and one atom being partially positive.
Well, you may have read in textbooks this kind of definition for hydrogen bonds, that they're the weak attractions between partially positive hydrogens and partially negative oxygens or nitrogens. You may not really get that because you know what ionic and covalent bonds are, but how does that fit into this? Hydrogen bonds are weird category bonds all kind of by themselves because unlike ionic or covalent bonds, which hold individual atoms together to form molecules, hydrogen bonds are typically weak attractions between two different molecules that hold those two different molecules close to each other. Now, how does this work? Well, it's all based on this quality that atoms have called electronegativity. In short, electronegativity is essentially how strongly does that atom pull on its electrons. Now, carbon, here I see a methane molecule, CH4. It has roughly the same electronegativity as the hydrogens that are bound to it, indicated by these black lines. Because it has roughly the same electronegativity, the two electrons here that form this bond are shared equally between the carbon and the hydrogen. Same over here. Oxygen, on the other hand, is an electronegative strong one. So it tends to pull the electrons much closer to it and further away from hydrogen, which is too weak to hold on to those electrons very well. So these electrons spend most of their time orbiting around the oxygen, very little time orbiting around the hydrogen. They are essentially only having visitation rights on the weak end as opposed to equal co-rights. So what that means is that these negative electrons tend to spend a little bit more time around the oxygen than around the hydrogen. That makes this oxygen slightly negative. If it's slightly negative, that means this hydrogen here is slightly positive. Now, scientists don't like writing stuff that means it's easy to understand. So they use the Greek letter delta, lowercase delta, to represent this slightly. I've always thought of it as kind of this weirdly cursive S, so I just think sorta. So here's my partially positive hydrogen, or or slightly positive hydrogen. So slightly positive, wait a second, this is slightly negative, but I know that water is a neutral atom, or neutral molecule, so it's got to be, yes, you guessed it, 2 slightly negatives. All right? Now, how this comes into play is, here's another water molecule. This is sort of positive, this is sort of positive, this is 2 sort of negatives, this is sort of positive, this is sort of positive, this is 2 slightly negatives. So what happens is that as this water molecule is floating around, this water molecule over here, this slightly positive, slightly negative, I'm slightly attracted. You form this weak attraction between these 2 molecules. Similarly, this water molecule over here, its hydrogen is going, hey, you're sort of attractive, and so we have our weak hydrogen bond there. This is extremely important in many ways because you may think of this as big whoop-de-doo, but it's actually a very big whoop-de-doo in biology because this influences tons of things, especially water. Now, you may have studied water in chemistry and learned about all of its wonderful properties, most of which are due to hydrogen bonding. For example, water is extremely hard to get it to boil. It takes a ton of energy. Why is that? Why does it take so much energy to turn it into a gas? That's because all the other water molecules start trying to cohere, trying to stick to the water molecules that's going away, pulling it back, kind of like molecular Velcro. It's really hard to get it to go away. It takes a ton of energy. This same quality of water, this cohesiveness, is how a tree is able to evaporate water from its leaves, and by cohesion, it's able to pull water molecules all the way down from the bottom of the tree and the roots pulling the water in from the soil. Another ability that water has is adhesion. It tends to stick to things. Here's a standard paper towel. I put it on my hand and it starts to fall. No big deal. Why? Gravity. If I get it wet, on the other hand, add some water. Now, I will show you some magic. Dun, dun, dun. So, same paper towel, all I've done is add water, which should make it heavier so it should fall faster, right? Unless Galileo was right. Wait a second, it's not falling. Well, eventually it does. Why? Did I generate anti-gravity here? Why did it stay? Because of hydrogen bonds. The water molecules were binding and sticking to the molecules that make up the paper towel, and also binding and sticking to my hand, so acting as a molecular glue. Now you may be thinking, okay, so we can do some evaporation stuff. So it's just water? No, it's more. Proteins hydrogen bond all over the place, and this gives them many of their abilities to form different shapes. It even causes the double helix of the DNA to spiral up and hold together. It is involved in so many things that this is a trick that I've taught my AP biology students. Whenever I call them and they don't know the answer, an answer that they can always pull out of their pocket is it's due to hydrogen bonds. And chances are it's right. If your teacher is one of those really annoying teachers who knows lots of stuff and he's really smart and knows a lot, and he calls on your, just say, well, it's probably due to hydrogen bonds. And if he's smart enough, he'll be able to invent a way that, yes, it is due to hydrogen bonds.
How come some insects are able to walk on the surface of a pond, but you quickly sink to the bottom when you try to walk on water? And why do lakes freeze from the top down in winter? In a word, the answer to all of these questions is polarity. Water is a simple molecule made up of 1 oxygen atom and 2 hydrogen atoms, but it is essential to life. In fact, water makes up approximately 60% of the adult human being's body weight. The polarity within those water molecules gives this common substance the properties that make it unique and life-sustaining. Polarity refers to the unequal sharing of electrons within a molecule. For water, the bonding between the oxygen atom and 2 hydrogen atoms within a single water molecule is like a tug of war between a big, strong football player and a cute little toddler. Oxygen is a larger atom with more protons in its nucleus than hydrogen. These positive charges are like a person's physical strength. They are able to attract the negatively charged electrons in the bond, just like a strong individual is able to overpower a weaker individual in a tug of war. So, oxygen is able to attract more than its fair share of electrons. Because hydrogen is smaller and has less strength, or fewer protons, it loses the tug of war, and attracts fewer than its fair share of electrons. So the oxygen in water behaves as though it's negative, and the hydrogens behave as though they're positive. The bonds within a single water molecule are called polar covalent bonds. Covalent means that the electrons are shared. But, as we just learned, polar means that these electrons are not shared equally. In water, the oxygen acts negative, and the hydrogens act positive. Since negative and positive attract, that oxygen is attracted to the hydrogen atoms in neighboring water molecules. A special type of bond forms between water molecules, known as a hydrogen bond. Hydrogen bonds don't just happen in water either. They can form between a water molecule and different substances that are polar or ionic. Water's ability to stick to itself is called cohesion, while water's ability to stick to other substances is called adhesion. Now, think back to the initial questions. First, why are some insects able to walk on water? Surface tension, due to hydrogen bonding, creates a thin film on the surface of water that gives enough resistance for super light insects to walk on. You can't walk on it because the hydrogen bonds aren't strong enough to hold you up. Why does ice float on top of liquid water? For most other substances, the solid state is more dense than the liquid state. But that is not the case for water. Hydrogen bonds keep water molecules farther apart in frozen water than in liquid water. The farther apart the molecules are, the less dense that solid is. So ice is about 9% less dense than water, which means it floats on the top. That's why lakes freeze from the top down and aquatic life is able to survive through a cold winter every year. It is the polarity of the water molecule and the resulting hydrogen bonding that account for water's unique properties. So, the reason that water is so special, from inside your cells to the world's oceans, is simply because it is a polar molecule.